Okay, I haven't had much sleep, all right? I don't really know where I am, okay?
You're here.
Yeah. So, reminder, why we think I'm not Stefano Profumo, he's a lot better looking than I am. If you wanted to see Stefano, feel free to leave now. I will not be offended, okay? But his flight got cancelled, so I'm going to talk about why we think dark matter exists, indirect detection of dark matter, direct detection of WIMPs, some particle models of WIMPs which are still healthy in September 2013. Evidence for dark matter, I don't need to go over this with you guys. Well, I will. The universe is expanding, but we know from nuclear synthesis that only 4% of the universe can be baryons. What's all the rest? If you look at the CMB, the chi-squared gets worse by something ridiculous, more than 200 if you don't include dark matter, which makes the plasma heavier, changes the oscillations. As long ago as 1933, Fritz Zwicky realized there was a problem with the virial theorem, that the coma cluster, the galaxies are moving too quickly. We've got things like the bullet cluster, which you can't explain, the gravitational lensing, unless you've got dark matter. Well, some people claim they can, but... And of course, we've got spiral galaxies. If you look out in the outer parts of spiral galaxies, they're rotating a lot faster than they should do. So that's all these things point to there being some invisible mass that we can't see. Lensing also suggests the presence of dark matter. So WIMPs work. So WIMPs are particles which are, there are either WIMPs are their own antiparticles or there's as many WIMPs as anti-WIMPs. And they're in thermal equilibrium in the early universe, and their self-annihilation cross-section is roughly given by the electroweak scale. And if that's the case, then you run time forwards, and when they go out of equilibrium, you end up miraculously with roughly the right amount of density to explain the amount of dark matter that we require in the universe for a wide range of masses. And this means that we sort of know what the WIMP self-annihilation cross-section has to be, because in order to end up with the right relic abundance, we know what the self-annihilation cross-section has to be. And that leads us straight into WIMP indirect detection, because if they were annihilating in the early universe, they'll be annihilating today, and we can try and see the signals of those annihilations. So dark matter self-annihilation, you get dark matter particles, WIMPs come in, they annihilate with themselves, and then they produce standard model particles, and we want to see the signals of those standard model particles. The rate at which dark matter annihilates with itself is given by, we think we know this self-annihilation cross-section. We've got some prejudices and ideas about the mass of the dark matter particles, and in particular, if they are WIMPs, they have to be roughly of the order of, GeV to 1,000 GeV or something. But the question is, how well do we know the density? Because the density squared obviously determines how often these things hit themselves. And in particular, we expect the density to be greatest at the galactic center, or the center of galaxies. So this is a dark matter simulation, the Aquarius simulation. This is logarithm of rho times r squared. And you can see that basically it's fitted well by a functional form like this, which is called the Ionasto profile, which suggests that the dark matter in the center of galaxies is a lot more dense than it is in the outer parts of galaxies. So in principle, you would want to look in the center of galaxies to see how much the dark matter annihilating with itself and producing a signal. Now, the typical slope, so if we say that we say this thing gamma is minus d log rho by d log r, it tells us how steeply the dark matter goes down from the center. As we move away from r equals 0, how steeply does the dark matter density go down? And we think, when you include things like baryonic contraction, that you expect a gamma somewhere between 1 and 1.7. Now, this is the luminosity that we expect from the center of the galaxy in ergs per second. An erg's about 1/4 of a TeV. That's the solar luminosity there, right? So, and this here, shrunk, is on the same scale. This is the actual astrophysical stuff that we can see from the center of the universe on the same scale, center of the galaxy. I told you I haven't got much sleep. It's going to happen again. Center of the galaxy. On the same scale. And you can see that the astrophysical background that we expect is very similar to the amount of luminosity we expect from the self-annihilation of dark matter, which is quite a heavy coincidence because the origin for these two luminosities is completely different, right? So here's Fermi's view of the galactic center, that's north. So you can see, there are some gamma rays concentrated on the galactic center, but being a gamma ray telescope is a bit like being a short-sighted man in a dark room. There are not many gamma rays, and you don't have a very good resolution. There's lots of other stuff down there as well. So there was this interesting paper which has Fermi detected dark matter annihilation at the galactic center. So what you can do is you can separate this gamma ray flux from the galactic center into annuli moving outwards from the galactic center. And then you can model the gamma rays that you expect from astrophysical sources. So from the bulge and from the disk, and then you get the total. And these authors, Hooper and people, have suggested that you get an excess of gamma rays in the central section. There are too many gamma rays coming from the central section, more than you expect from the background gamma rays. And you don't see that in the outer parts, okay? So they claim that this could be evidence of dark matter annihilating with itself. But this is very far from being universally agreed or taken seriously, right? It's just a very interesting thing. So this is the spectrum that they see as we go up in energy here. These are the photons that they see that they think might come from dark matter. But for example, there's an alternative explanation here by these people and Chernyakova et al. So they just suggest that these are high energy protons that are accelerated by the supermassive black hole at the center of the galaxy. And the diffusion coefficient is such that the high energy protons manage to stream away from that region without any difficulty, producing a nice power law that's observed at high energies. But the lower energy protons get buffeted around by turbulence in the magnetic fields, and they end up concentrated in the central region, and consequently you get this different shape of spectrum there. And they can fit the same data using these protons banging around and producing gamma rays in this way. So there's a nice little bit of evidence there, and we need to understand the astrophysics more to understand exactly what's going on. Then there's this looking for lines business. So Fermi can also look for spectral lines. So if you like, a smoking gun signature of dark matter is you get two dark matter particles coming in and annihilating, and every so often they will go into two photons, okay? And then the photons, of course, will carry away the rest mass of the dark matter, so you should get a monochromatic line. Usually, most of the photons come from secondary processes, so you get a spectrum, but you can get a monochromatic line. So this is an analysis done by Veniger. And what he's done is he's analyzed the Fermi data, and he's for different kinds of density profile, and for each choice of density profile, he's chosen only those pixels that together will maximize the overall signal-to-noise ratio. And then he's looked for lines. And he's seen this line by looking at the center of the galaxy, which corresponds to about 130 GeV. And it's reasonably statistically significant. The statistical significance depends on which density profile you look at. So this has caused an enormous amount of interest. But now it's not quite clear exactly what's going on, because recently Fermi have looked at the same thing in more detail. They tend to do things very thoroughly and take a long time to do them, which I suppose is a very good thing. And they've seen a bump in the energy response of Fermi in a similar energy, even when they're looking at the Earth limb. And consequently, it's clear that a lot more work needs to be done to understand the response of the instrument and also understand exactly what's going on to see if these Fermi lines can be taken seriously. There's this other issue, which comes from a completely different direction, which is related to indirect detection, which is that we don't really know how much dark matter there is at the center of the galaxy. And people who do simulations of galaxies are putting baryons into their simulations, and they're finding all sorts of strange things happening. Previously, it was thought that baryons would shrink into the center of the galaxy by losing energy and emitting radiation, and shrink into the middle and form a big potential well, which would actually bring in the dark matter and make it even steeper at the center. However, they're doing things with gastrophysics, so they're having supernova explosions go off in their simulations, which redistributes the baryons and pushes them out. So you get the dark matter adiabatically being contracted and then non-adiabatically being shocked, so the gravitational potential well is doing all sorts of things. And the result seems to be that sometimes you don't end up with such a steep amount of dark matter at the center of the galaxy as you might like. So here's a bunch of simulations. This is the mass of the galaxy in solar masses, and this is something that comes from CDM. So here's some simulations. This is alpha at 500 parsecs from the center of the galaxy. So alpha is how steeply the density is going up as you approach the center of the galaxy. And of course, if alpha is going up more steeply, you're going to have a bigger signal. So if it's more negative, you're going to have a bigger signal from indirect detection. So if you only have dark matter in your simulations, you get values like this. But if you include baryons in your simulations, it seems to flatten out the dark matter in the inner parts of the galaxies. And that might be a big problem for people who are hoping to do indirect detection. So I just wanted to throw that in there, not to be too pessimistic, but anyway. So dwarf spheroidal galaxies are very interesting objects. So you're looking at the center of the galaxy. If you're looking at the middle of the Milky Way, there's an enormous amount of stuff down there, and it's very difficult to separate the signal from the astrophysics. But if you take a dwarf spheroidal galaxy, you don't really have the same problem because they've got a very big mass-to-light ratio, which means there aren't many stars in there. There's a lot of dark matter. So in principle, any signal from the annihilation of dark matter shouldn't be hampered by there being lots of background from astrophysics, okay? But they're very small, and they're reasonably quite far away from us. So they're in orbit around the Milky Way, so they're not that far from us, but they're quite dim. So in practical terms, they're quite far from us. Now, these guys can tell us lots of different things. Not only can they tell us, if we understand the inner density profile of the dark matter in dwarf spheroidals, how quickly that density goes up, not only will they tell us the expected annihilation signal from WIMPs, they could also tell us things like, is dark matter self-interacting? Or is dark matter warm or hot? Because if dark matter is self-interacting or warm, it's very difficult for the dark matter to concentrate really at the center. If it's got lots of kinetic energy, it will redistribute itself. And if it's colliding with itself, the pressure will redistribute itself, a bit like a star, you know. The thing is, so you can do in principle, you can do lots of sexy new physics with dwarf spheroidals if you can figure out what the density is. That's a function of radius. However, you've got the same boring health warning, and that is that gastrophysical effects can also change the density of dark matter in dwarf spheroidals. So that's baryons falling into the middle and then going off as supernovae and what have you, and redistributing the dark matter. But anyway, here's the most obvious thing that you can do with dwarf spheroidals. You can work out how many gamma rays you expect from the dark matter annihilating with itself. So here's some fits to the data. So this relies on you understanding how much dark matter there is in the dwarf spheroidal. Then you integrate the rho squared times sigma v to get the number of gamma rays that you're going to get. And you can see that this is 3 times 10 to the minus 26 centimeters cubed per second. So this is what you need for WIMPs annihilating with themselves. And you can see if you stack up all these dwarf spheroidals that are going around the Milky Way, we're getting below that line for low mass WIMPs, okay? So that's really interesting. So we're not seeing gamma rays when we should see gamma rays. Now, there's a caveat here, and that is we don't know exactly what the density profiles of these dark matter, the dark matter in these dwarf spheroidals are. But that shouldn't introduce a massive uncertainty. But nevertheless, it's important to understand it. And again, baryonic effects might be important. So the baryons, first of all, sink into the middle, and they pull the unsuspecting dark matter in, and then they go supernova, and the potential disappears, and the dark matter, which is virialized, flies off. So it's a bit messy. So there's quite a lot of people who, well, I'm talking about it because I'm one of the people, who's trying to understand how you work out how much dark matter there is in dwarf spheroidals. And the way that you do that is you use the Jeans equation and then you use the line of sight stellar dispersion. So we need to obtain m of r, okay, but we don't know what so this is the Jeans equation. So sigma t is the velocity dispersion of stars. You've got some velocity dispersion, which is like approximately a Gaussian, and you've got one which is perpendicular to the radial vector, and you've got one which is parallel to the radial vector, sigma r. So this beta is the anisotropy parameter. And we don't know what this is. We only see a even for stars, when we can see the stars, we don't know what it is, because this is radial, and we only see a projection of this. So we have to marginalize over this. So these are scenes from the spherical triaxial working group at the Gaia Challenge 2 weeks ago in the University of Surrey. This is Walter Danon giving me a dirty look for taking a photo of him. And this bunch of people all got together to see if we could understand what the density of dark matter was in some simulated dwarf spheroidal galaxies. And we've all got different techniques, and some of them are more complicated than others. So our technique, which I'm just going to plug very quickly, is a new method to constrain the density of dwarf spheroidals. As well as using the second order in the velocity dispersion, we're also using the fourth order. And the green is the way that we recover the red line, which is the underlying fake data. So we create a fake dwarf spheroidal, and we produce some stars that are moving around in this fake potential well. And we try to understand how quickly we can, how well we can reproduce the potential well they're flying around in. And you see the blue lines is when you don't use only the second order information, but if you include higher orders of the Jeans equation, in other words, if you take into account the kurtosis of the velocity dispersion, you can get more information. Now, So this is an example which worked really, really well, okay? But don't worry, they don't all work really, really well. So if you only do the second order now, the dotted line is d log m by d log r. So that's the way that the mass goes down as a function of radius. It tells you whether you're chord or cusp. So this is a chord one. And you want to find out if this is a chord or a cusp dwarf toroidal. If you only use the second order information, you get this. But if you use the fourth order information, you get a much better reconstruction of the density. Now this one works well, but it doesn't always work so well yet. So me and Tom Richardson are working on that, and he's giving a little talk on this in the Galaxy session later in the week. So that's an active, dwarf toroidals are really important laboratories for dark matter physics, and trying to understand what the density in dwarf toroidals is a sort of sub-subject that quite a few people are engaged in. So positrons, moving on. Okay. Pamela and AMS both see positrons. So these are both things that are in orbit around the Earth, and they see anti-electrons, more anti-electrons than you would expect. You do expect to see positrons, so you get cosmic rays coming in, high-energy cosmic rays coming in, they hit the galaxy, and then you get cascades, and as part of those cascades, you get positrons created. Now, the thing is that you expect those cascades to give you a nice spectrum that keeps on going down all the way there. Now, what Pamela noticed, the blue data points, was that actually you were getting a lot more positrons than you expected as a fraction of the total number of electrons and positrons. It was going up. So everyone's very excited about this, but it wasn't really clear that this very small collaboration, this very small box, which was attached to the size of a Russian weather satellite and only had one way of discriminating things, people didn't really know if they should trust it. But then AMS, which has been called LHC in space, it's a massive, great, wonderful detector which has been bolted to the International Space Station, has shown that the Pamela people got it spot on. And now AMS are picking up they're taking the next leg of the relay, and they're trying to go to higher energies and reduce the errors. So these positrons, where do they come from? Are they a signal of dark matter? Well, they could be a signal of dark matter. It could be dark matter annihilating with itself, because if it annihilates, it will produce as much matter as antimatter. So people have shown that you can model these positrons by the annihilation of dark matter. The trouble is that there are so many positrons that if we just take that cross-section that I was talking about, it seems impossible to get as many positrons as is necessary to explain the signal from AMS. So this is what you call the boost factor. So if you've got a problem where you need more annihilations than what you've got, which is what we've got with the positrons, you can do things like this. So we know the freeze out, the self-annihilation cross-section in the early universe. You can come up with some reason why the self-annihilation cross-section today is a lot bigger, which would result in a lot more self-annihilation. And we know that the average density is not the relevant thing for self-annihilation. It's the average density squared. So if you say that there's actually quite a lot of local substructures, so lots of like little clusters of dark matter, then you have to take the average of the density squared. And that could be quite different from the average of the density squared. So, but however, people have done simulations and they've shown that we're quite deep, sort of down in the middle of the Milky Way. The Milky Way, as far as dark matter is concerned, is a big, massive thing. And down here, we're right in the middle of a potential well. And any of this substructure that's made it down here should have been tidally disrupted. And we know that positrons don't get very far because they lose energy fairly quickly. So the positrons that we're seeing have to have been created within about a kiloparsec of the sun. Okay, so that doesn't seem to be a viable thing. So one of the ways that so you can think of different ways to make the cross-section different today as to what it was in the early universe. If you've got S-channel ionizations, you've got a problem because the cross-section in the early universe should be the same as the cross-section today. If you've got P-channel annihilations, it can go the wrong way. So we need something else to enhance the cross-section. Now, if we had dark matter that was very heavy, then in principle, you would get dark matter particles pulled together kind of semi-classically by the exchange of W and Z bosons to enhance the annihilation cross-section. So some people took this idea, this is called Sommerfeld enhancement, they took this idea and they ran with it. And in general, you can consider a much lighter, so this is a dark force in between dark particles, okay? A much lighter GeV boson, for example, weakly coupled. And that would make the dark matter sort of classically attract itself, so you would enhance the self-annihilation cross-section. Now, some people have said that that's a problem because in the early universe, when the dark matter is really moving very, very slowly, you're going to get a lot of self-annihilation because this happens at very, very low velocities. So in the early universe, the dark matter was not moving very quickly, because its motion mainly comes about through it falling into potential wells, because it's cold dark matter. So in the early universe, when it is moving very slowly, you would think you'd have problems for the first structures that are formed. So for example, I refer to this work by Kamiokowski and Profumo. So Profumo's the poor guy whose flight got cancelled. I'd tell you, he's good looking, isn't he? So that's one way that you can possibly boost the self-annihilation cross-section to get nice positrons that could fit the AMS signal. The other possible way that you can get it is just astrophysical origins of electrons and positrons. So this is supernova remnant, a pulsar flying around. It could produce antimatter, and that could come to us. Now, AMS, of course, now they're getting massive statistics, and they've only just started their job. So that's fantastic that we're going to get lots more data about this. One of the things that they've tested is whether, if the excess has got a particle physics origin, if it's coming from dark matter, it should come from all over the sky. If it's coming from a pulsar, you would expect it to come from the direction of the pulsar preferentially, okay? At the moment, you can't tell, because at the moment, if you look at the dipole anisotropy, it's less than 3% at the 95% confidence level. However, our missing speaker, I feel sorry for the 3% anisotropy is still larger than the anisotropy you expect for a single pulsar. So you're really going to have to measure this anisotropy very, very carefully if you're going to distinguish between a pulsar and dark matter. Okay, so indirect detection conclusions. So we've got hints from the galactic center of low-mass WIMPs, but they're just hints, but they're exciting. There's other astrophysical explanations exist. There's hints from the galactic center of gamma-ray delta functions, but we need to understand this better. Understanding the density profile of dwarf spheroidals is important for a variety of different reasons. The anomalous positron-electron flux might be a signal, might not be a signal. But there's lots of work being done, and we're going to get updates on all these things over the next couple of years. Just a quick aside, self-interacting dark matter, the motivations are, if you've got these theories of Sommerfeld enhancement, then you've got this idea that you've got a dark sector with bosons flying around, so you've got some dark forces. Then you've got this missing satellites problem. In lambda CDM simulations, you get lots of little dwarf spheroidals, and we don't see anywhere near as many dwarf spheroidals in reality as what you see in simulations. Then you've got the core versus cusp problem. Dwarf spheroidal galaxies seem to have the density goes to a constant density as you approach the core, as opposed to keeping on going up as you would expect in a cold dark matter simulation. And then you've got this too big to fail problem. The biggest dwarf spheroidal we observe is not as big as you get in simulations. Now 2 and 3 can potentially be solved with this baryonic gastrophysics that I was talking about. 4 might be solved with baryons and a bad estimate for the Milky Way mass. 1 could just be plain wrong. However, we can test it. So let's just assume that, all these things are things that we should worry about and test the self-interaction of dark matter. So it's not as simple as it appears to be. So for a potential, like a Yukawa potential like that, you expect the perturbative cross-section, which is easy to work with. You can write it down and then you can stick it into your simulation. However, it's been shown that if you want to do it for real astrophysical systems, things get non-perturbative. And you need to use these different expressions. So you really have to do computer simulations of particles moving around in each other's potentials and whizzing around 3 times before they zoom off. And then you have to fit it all numerically. And then you have to try and somehow stick that or attach it to your simulations in some way that allows you to take all this stuff into account and figure out if there is self-interaction of dark matter. So besides these difficulties, people are trying to constrain such models using objects such as the bullet cluster, which you've heard the dark matter is flying through itself, so if it's self-interacted, you get a constraint. So I won't talk about that. But also this guy, the elliptical galaxy NGC 720, which they've managed to say that the dark matter itself, the dark matter halo, is triaxial. So it's not spherical. And that allows you to put a constraint on it, because if it was bashing into itself, then it would end up being spherical. Typical constraints from both this and the bullet cluster give you something which is about a centimeter squared per gram. It's about 10 to the 12 times the weak interaction. It's quite a big cross-section in terms of the particle physics which is going on in the standard model sector. So, but this is I just wanted to mention this because quite a lot of people are interested in it at the moment. Moving on, direct detection of dark matter. Every so often, a dark matter particle will hit you. And when it hits you, you know, we think in every cubic meter there's about 1,000 dark matter particles. They're all moving about 200 kilometers per second. When they hit you, they leave a bit of energy, like a KeV worth, an X-ray worth of energy, you know. And people are trying to look for these energy. You know, it can produce, if you've got a cryogenic system, it can heat up the cryogenic system. People look for the temperature change. It can produce, if you've got a scintillating system, it can give you a photon. People look for the photons. It can give you ionization. There's lots of different ways to look for this. Of course, the backgrounds are awful, but people are brave, and they do it, you know. So if you want to know the counts per kilogram per detector mass per KeV, you have to do this integral. So what you're doing here, I've stolen this from Thomas Schvetz. What you're doing here is, in the rest frame of the galaxy, you've got a distribution of dark matter velocities, okay? Let's say it's a Gaussian distribution in the rest frame of the galaxy. But we are moving around the galaxy at 200 kilometers per second. So let's say that I've got a detector which, if I hit it such that I get a recoil of 3 keV, it'll make the detector go bing. Then I need to integrate over all the parts of the velocity distribution that are outside this purple line. But if my detector's less sensitive, and I hit it, I need a recoil energy of 10 keV for it to go bing, then I need to integrate over this much smaller region out here. So that's the game. Different detectors have got different recoil energies, and if they're made from different atoms, you're going to get a different recoil energy when it gets bashed with the same velocity. So it's a bit of a complicated game. Here's the state of the art. Xenon 100 has got the tightest constraint on the cross-section for a dark matter particle hitting a nucleus. It's something times 10 to the minus 45 centimeters squared, about 55 GeV. But as you can see, up here, there's a lot of funny stuff going on. Okay? So, right, okay. So CDMS, okay, has detected 3 events with a 5.4% probability. They claim they've got a 5.4% probability. And they interpret that as it being a signal at 8.6 GeV. So 8.6 GeV dark matter particle. Now the trouble is with that is that Xenon 100, which is a bigger machine, it rules out this area. It says that you can't have a dark matter particle with that mass and that cross-section, otherwise you would get signals there. So how do we know that astrophysics isn't responsible for these differences? So there's lots of spherical sources of astrophysical uncertainty. There's non-spherical sources of astrophysical uncertainty. If we just take the spherical sources of the astrophysical uncertainty, again, we're solving the Jeans equation, but now not for stars, we're doing it for dark matter. If you fit things like the rotation of the galactic disk, the local rotation, its derivative, and the motion of distant blue stars, and the motion of the Milky Way satellites, and then you stick it all into an MCMC, you get a prediction for the local density, which is quite rigid. Now, the funny thing is, we don't know how much dark matter there is at the center of the galaxy, and we don't know how much dark matter there is in the outer parts of the galaxy, but it turns out we're living in a kind of sweet spot, 8.5 kiloparsecs from the center of the galaxy, where you do have a very, very good knowledge of the amount of dark matter that's around us. It's about 0.3 GeV per centimeter cubed. And we've also got a fairly good understanding of the velocity, the escape velocity of the galaxy, okay? It's somewhere around 560 kilometers per second. So what you do is you can crank the handle and you can work out what that means. What do we expect for the velocity distribution in the region close to the sun? And you find that we expect something like this. And you take all these things into account. You include non-Gaussianity, the possibility that the distribution of dark matter is non-Gaussian, which you expect it to be non-Gaussian because it's not an ideal gas. And the variation due to all these effects is not that huge, actually. It's maybe an order of magnitude over here. But as you get to very, very small masses, the variation becomes massive. So this is the region here. The left-hand wall of this sensitivity, where xenon rules out CDMS, is very, very sensitive to the escape velocity. So perhaps if we've got the escape velocity wrong, you might tell yourself, you could move the xenon in that direction, and CDMS wouldn't move as quickly in that direction, and we could explain the two signals together. Because for low-mass WIMPs, if you want to make a detector go bing, you have to hit it very, very hard to get the same recoil energy so that you've got enough recoil energy for the detector to be sensitive to it. So that's why it's sensitive to the escape velocity. However, it doesn't necessarily help reconcile, for example, CDMS and Xenon 100. Now, this is schematic. If I set the escape velocity to 450, then the fit, some measure of how good a fit it is 0.7. But if I change it to 650, the fit doesn't get any better. So the thing is that if you start messing with the escape velocity, not only do you shift the CDMS region to the left, but also you make the xenon a better detector. So the things, generally speaking, if you want to explain CDMS and xenon together, you have to do some funny stuff. So these astrophysical issues affect different experiments in different ways. Spherical uncertainties are much worse at low masses. In order to really convince ourselves that we've got a signal as well, we would need significant detection at multiple detectors. To one, get a signal in that we believed in the first place, and two, to measure the mass. I just wanted to put an advert in here that the UK dark matter community are trying to, they're putting in a bid to join Lux Zeppelin. And if you look at the sensitivity of Lux Zeppelin, it's going to go down to 10 to the minus 48 centimeters squared. So over the next few years, things are going to change fairly rapidly. I've got 2 minutes, okay. I did put a lot in my talk. It was late. Right. Some particle models of WIMPs which are still healthy in September 2013. So we've heard that the constrained minimal supersymmetric standard model, which has got neutralinos in it, is under pressure. So this is the evolution of time of the CMSSM. What you want to see here is blue parts, because dark blue is a good chi-squared. And as you become progressively green and more yellow, you've got a bad chi-squared. And as we post LHC and Xenon 100 in 2011, you see the colors getting worse. Post the discovery of the Higgs, they're getting worse again. And then Xenon, updated limits from LHC and Xenon, they're getting even worse. And if you look at the direct detection, pre-LHC 2008, there was lots of nice blue regions. Post-discovery, you've got constraints from the Higgs, and you've also got constraints from Xenon 100, which has ruled out a lot of this parameter space. But so the CMSSM is under pressure, but is that because it's too CM and not enough SSM, right? Is it too constrained and too minimal? So some people are just allowing things to be less constrained. So this is the PMSSM, where you allow all these different parameters to vary. And you can still get some nice regions. So one of the things that they look at is how fine-tuned the theory is. And you can get both low-mass dark matter particles, which could in principle be consistent with CDMS. And in general, you can still get some dark matter particles that haven't been ruled out by the existing limits, which is this Xenon 100. You've still got some good regions down here where you've got a cross-section which shouldn't have already been detected, which isn't too fine-tuned. So there's also Higgs portal dark matter. I might do a talk in the parallel session this afternoon if I haven't collapsed on that. But my conclusions are, for particle candidates, as the LHC probes the electroweak scale, all WIMP models are facing tighter constraints, as one would expect, okay? The simplest models of SUSY are under severe pressure, but it'll be some time before SUSY itself can be ruled out as the origin of dark matter. And many more, much simpler models are being studied in light of the new data, which will also face welcome pressure in the next few years from the LHC and direct detection experiments. So in conclusion, indirect, direct, and collider experiments are severely constraining the parameter space of WIMP models, and this is good. So thanks very much for listening.
Okay, questions?
What is Dama Liber detected?
Yeah. So DARMA is an experiment with a very, very low energy threshold, lower than most other experiments, goes down to about 2 keV. And they've got very good statistical significance for an annual modulation, which so as the Earth goes around the Sun, you're integrating over a different region of the background, okay, of the velocity distribution. And this, in principle, can explain the fact that you've got, when we're moving most quickly into the WIMP wind, it's June the 2nd, and when we're moving least quickly into WIMP wind, it's December the 2nd. And this annual modulation could, in principle, explain why DARMA is detecting dark matter, or potentially detecting dark matter. They're only detecting dark matter in their lowest energy bin. So in principle, you could have a very light dark matter particle which was giving you a signal, but it's very, very difficult to model it. The way that I would try and model it is by putting a stream in. So if you imagine there's a stream coming from the same direction that the sun's moving in, and there are streams of galaxies moving, there are tidal streams with stars in them moving around the galaxy. If you had such a stream coming towards us and we were moving into it, then in principle, you might, and they were very light dark matter particles, but they had a huge velocity, something ridiculous, like 1,000 kilometers per second. Then in principle, as we moved into it and came out of it, you could get a signal. If you don't do something like that, it's very difficult to understand how this can be explained without xenon going off, because they claim their low energy resolution is such that they would be able to see this. So if you take xenon, and I mean, xenon wasn't designed to look at those low energies, but since it's become such an interesting area, they've spent a lot of time trying to understand their detector in this, right at this bottom energy range, to see if these low mass dark matter particles are acceptable. And they claim that they can rule out Dharma. And so if you really take them seriously, then I have no idea what Dharma's detected.
It has detected something significantly
Yeah.
very high.
It has detected an annual modulation. You're absolutely right. The statistics are very, very high. Whether that's dark matter or not, we don't know.
Okay, maybe time for one quick question if there's any. Or no? Otherwise, let's thank Malcolm again.